Hello again, my name is Tom Irvine, and our subject for today is sine vibration. So here's a simple plot. It's amplitude versus time, and it's a single cycle of a sine function. So the mean value is going to be equal to 0. That's where the sine function begins. And its peak positive value is 1, and its peak negative value is -1. That's just for the sample here. So there's several ways we can characterize the amplitude of this signal. There's the peak-to-peak amplitude, which is often used for displacement. There's a zero-to-peak amplitude, and then there's the RMS, which is root mean squared. Now later on, we're going to be talking about fatigue analysis, and when we get to fatigue, amplitude will be 0 to peak, and the range will be the peak-to-peak value. So let's think for a minute, what is an RMS value, and how does that relate to a standard deviation? So an RMS squared equals a standard deviation squared plus the mean squared. So RMS is equal to 1 sigma, assuming 0 mean. Or generally speaking, we can say that RMS is always greater than or equal to the 1 sigma standard deviation. Now, in the world of vibration analysis, the mean value is typically 0, and that was the case for the previous sine function. So we are in the habit of using RMS and 1 sigma interchangeably. But just be aware of the equations on this slide. Does sinusoidal vibration ever occur in rocket vehicles? And the answer is yes. There's a couple different scenarios here. So solid rocket boosters, they have something called a thrust oscillation, also referred to as a resonant burn. Now, not all solid rocket motors display this, but some do. So here is the space shuttle. It's been retired for 10 or so years now. But on either side was a 4-segment booster, which was a solid rocket motor, strap-on booster. And what happens is there's a cavity, an organ pipe-like cavity in that solid rocket motor, and standing pressure waves get set up under high temperature gases, and there could be some vortex shedding driving those standing waves, and that becomes a sinusoidal oscillation at the natural frequency of that cavity. For the space shuttle then, the 4-segment booster had an oscillation frequency of 15 hertz, that was sinusoidal. And the Ares 1, now the Ares 1 never actually flew, but it was a 5-segment booster, and since it was elongated relative to the 4-segment, it had a lower pressure oscillation frequency down at 12 hertz. So there's a big concern back on Ares 1 that the crew capsule would be at the forward end, and that would be in line with this booster and its oscillation frequency there, that would be a problem in terms of the transmitted loads. Whereas on the space shuttle, you can see that the orbiters attached to this external tank, and then on either side of the external tank are the 2 solid rocket boosters, so that sinusoidal oscillation had a circuitous route to get into the orbiter itself. So that sort of mitigated that concern back in the space shuttle days. But it became a big concern for Ares 1. Ares 1 never did fly. The program was canceled. There was a Ares 1X that did fly, unmanned vehicle, but that had a 4-segment booster. Another thing that can happen, now it depends on what the internal cavity geometry is, but on some motors what happens is that cavity volume will elongate during the course of the burn, and as a result of that, then the pressure oscillation frequencies will decrease. So it all depends on what is the initial volume inside that cavity, that combustion cavity, and how does that volume change over the course of the motor burn. Another thing that we encounter is called Miko. So this is a Delta II vehicle. So Miko is an acronym for main engine cutoff, and it's a transient event. In the case of Delta II, it was at 120 hertz. And there was a concern because Miko could be a high force input to the spacecraft at the forward end of the vehicle, enclosed in the fairing there. So that the plausible explanation was that there was an instability in the combustion chamber as the liquid engine valves are closed and the liquid oxygen and fuel are depleted. So basically, you think of it as a hiccuping effect or a coughing effect. Sufficient main energy force is produced to drive the entire system, as seen by all launch vehicle instrumentation recording Miko event. So this Miko transient, the resulting sinusoidal vibration, was picked up by all the accelerometers throughout the vehicle. And it was actually occurring on every flight, although the magnitude or amplitude would vary from flight to flight. So there was some variation there, but it was expected on every flight. Now the Delta II is now retired, but it had a very successful history of putting satellites into orbit. So it's interesting, solid rocket motors have a thrust oscillation, potentially, and liquid engine systems, potentially, have a main engine cutoff issue. Upper stage liquid engines have SECO, second stage engine cutoff. Now here's some actual accelerometer data from a Delta II mission, and it was at the guidance section. This was presented at a conference. Now the x-axis is going to be time in seconds. The y-axis is carrying no units because I guess the data was considered proprietary or something to that effect. So at the conference I went to, we did not get to find out what the G levels were. Now this is not a pure sine, obviously. It's more of a transient sine, but it is fairly sinusoidal, and the dominant frequency is 120 hertz. And if you look real carefully, you can see there's a little bit of peak clipping going on. So the instrumentation range was not set as high as it should have been. But as clipping goes, it's fairly minor clipping. But yes, we're going to acknowledge there is some clipping there. So again, the concern was that this energy could propagate to the payload and be, well, there's a whole analysis called coupled loads analysis. So the coupled loads analysis for the payload would have to take into account that this Miko was going to occur on every flight. Now, liquid engines have another type of sinusoidal oscillation, and this is called Pogo. So Pogo is the popular name for a dynamic phenomenon that sometimes occurs during the launch and ascent of space vehicles powered by liquid propellant rocket engines. The phenomenon is due to a coupling between the first longitudinal resonance of the vehicle and the fuel flow to the rocket engines. Now, in reality, if we look at historical Pogo data, there are other types of structural resonances that can get coupled in with this instability as well, but the classic Pogo is the first longitudinal resonance of the vehicle. So the launch vehicle is vibrating basically up and down. Imagine you had a slinky that's vibrating with no constraints on either end. So here is a astronaut, Michael Collins. He's best known for the Apollo 11 mission, but he also flew on the Gemini program. So Gemini means twins, and there was 2 astronauts in each of the spacecraft for the Gemini Titan II missions there. And he wrote in a book, the first stage of the Titan II vibrated longitudinally, so that someone riding on it would be bounced up and down as if on a pogo stick. The vibration was at a relatively high frequency, about 11 cycles per second, and with an amplitude of plus or minus 5G in the worst case. Well, I really appreciate his preciseness about the parameters of this sinusoidal oscillation. And he was, in fact, an engineer as well as being an astronaut. So thank you, Michael Collins. So 11 cycles per second, we would call that 11 hertz, but it's all the same thing. And he's very clear on what the amplitude is. So we would say that the 0 to peak then is 5Gs. He said plus and minus 5G, and that means the same as 0 to peak 5G, assuming a zero mean. So what are the consequences of this Pogo oscillation? Well, in terms of the human astronauts, you might think, oh, it could make them sick or whatever, place stress on their bodies, and that's all very true. But the more immediate concern was blurred vision, because these astronauts had to pay attention to the instrument panels, and their vision became blurry due to the relative displacement between their eyes and the instrument panels is a result of this pogo oscillation. Now there's ways to mitigate pogo using accumulators in the propellant feed lines. We might talk about that later. But let's go ahead and take a look. What is the corresponding displacement for 11 hertz 5Gs? So how would we go about calculating that displacement? Well, I'm actually going to show you the equations in a couple, 2 or 3 slides from now. But let's go ahead and do Matlab script, and we'll take a look at how to do this using the vibration data GUI package. So you can open up the GUI package, and then you would go to the top middle, and there's a tab called Toolbox and Miscellaneous. Then you go down to Miscellaneous 1 and select Amplitude Conversion Utilities. And then we've got 2 options, Sine and SRS. We're going to pick Sine for today. And it'll be acceleration 0 to peak, and we put in 5Gs and 11 hertz. I should be using the mouse here to show you everything. We hit the calculate button, and we can see all the equivalent metrics. So it's 11 hertz sinusoidal frequency. The peak-to-peak displacement is a little over 0.8 of an inch. The 0 to peak is 0.4 of an inch. And corresponding velocity, corresponding G levels, we've got both the English and metric there. So yeah, that an astronaut experiencing a peak-to-peak displacement of 0.8 of an inch, yes, his or her vision will become blurry. Okay, here's a fun one here. This is a launch vehicle control system oscillation at stage 1 burnout. And this was a solid rocket motor type vehicle, acceleration G versus time in seconds. And we already talked about liquid engines have a Miko. Well, this is kind of, sort of, but not exactly the same type of effect, only it's happening with a solid rocket booster there. So there's an oscillating thrust vector control TVC system during the burnout of the solid rocket motor. So what happens is that the nozzle was gimbaled. That means it's a movable nozzle to provide steering for the vehicle, and it's controlled by a thrust vector control system. So there's a certain gain factors and control loops and algorithms and all of that. And the algorithm was assuming that during tail-off, the thrust was still at full level. So the control system would issue a command to the TVC to say, okay, let's do a yaw of, say, 1 degree. I'm just making that number up. And the vehicle was very sluggish to react because the thrust force was tailing off, so there's less moment available. So the control system and the TVC system just kept going and going and going, trying to steer the vehicle, and it was a tail wags dog effect. Now that's not a pure sine function, but it's fairly sinusoidal. And there's actually 2 sine functions superimposed. There is a 12.5 hertz, and then there's a 3 times integer harmonic at 37.5 hertz. There's also a stage separation event. You see it 92 seconds there. But this accelerometer, the location is not documented. I believe it was at the forward end of the vehicle. And this is a design problem because the whole vehicle could have gone unstable, or the force input to the payload could have been excessively high, caused damage to the payload. Happy to say that this was a successful mission, but it's interesting when we get this telemetry data back from missions, and there's a lot of hoopla in the press release of how glorious and successful the mission was, and then we get to see, oh, oops, we almost came close to losing that vehicle. So the fix was very, very simple. It was just to basically turn off the TVC system during the motor tail off. And I was the one that actually came across this data and had to go to the guidance navigation control engineers and make a case, and they didn't want to believe me at first, but eventually they did and fixed the problem. Here's something different, another acceleration time history, acceleration G versus time in seconds, also some flight telemetry data. And this particular vehicle had a gas generator that was operating at a particular time in flight. And the dominant frequency there is 1600 hertz. So the data was filtered from 1000 to 2000 hertz. And there was not pure sine, but fairly sinusoidal 1600 hertz sinusoidal oscillation, well, that was the operation of this gas generator. And the gas generator was driving a fin control system, an actuator for a reentry event. So when we get our telemetry data back, we do sometimes see these sinusoidal oscillations. This one was expected. The tail-off oscillation, the previous slide, was not. So we have to take a look at this data and scrutinize it, apply our critical thinking skills, and determine whether it represents an anomaly or normal operation. We also have to make sure that, say in this case, let's just say that there's a nearby avionics component. Well, it needs to be designed, analyzed, and tested to withstand 1600 hertz because of this excitation function there. Okay, we're going to do a fun little Matlab exercise here. We're actually going to generate a sine function. So we'll get out our Matlab, we'll go to the Generate tab, we'll go to Signal Index, and the second one down is sine, multiple sine tones, damp sines, and cosines. Then we hit the Perform Analysis button, or I think you might just double-click on that grayed area there. And our sine function we're going to generate today, so we're under this A tab here, the second row of tabs. It'll be a duration of 1 second, 50,000 hertz sample rate. So sample rate units are more properly samples per second, but it works to call sample rate unit hertz as well. That works just fine. We've got a couple of different types of sine functions we can generate, and cousins, and variants, and so on. So let's do a sine amplitude 1, and the frequency is 10 hertz. Now 50,000 hertz sample rate is much, much higher than 10 hertz, but there's a reason we're selecting such a high sample rate, and I'll show that to you in a minute. Phase angle 0, rectify is no, hit calculate, and let's generate a sine function and see what characteristics it has. So here is the sine function, and off to the left we've got acceleration g versus time in seconds. 1 second duration, it's 10 hertz there, so you could count the number of positive peaks and divide by time, and that would be 10. A more proper way to estimate frequency is to do something called the positive slope zero crossing rate. So the positive slope zero crossing rate is where the signal goes through the 0 point there, and we just count the number of occurrences and divide by duration, and that's the positive slope zero crossing rate. And when we get to more messy signals, that's better than just calculating the frequency as the number of peaks divided by time. Now let's take a look at this histogram. And the reason we had such a high sample rate relative to the frequency was so that we could get a smooth histogram. Now this histogram is rotated 90 degrees clockwise from what you're probably accustomed to seeing histograms. And the reason for that was so that we've got two subplots here. In each subplot, the y-axis is acceleration g minus 1 to plus 1. So that's on purpose. And then the x-axis of the histogram is counts times 10 to the third power there. So the histogram concept is very simple. We have to realize what this sine function really is. It appears as a nice continuous curve, but that's because there's dot-to-dot connection, like a child's dot-to-dot puzzle. In reality, this sine function is a series of points. In fact, altogether, there are 50,000 points. Now, the Matlab software, again, does a dot-to-dot connection with a straight line segment, so to our eyes, it appears as a nice sine function. It's really a series of dots, of data points. Now, imagine we go to the acceleration in g, and we come up with bins, B-I-N-S, bins, non-overlapping, probably going to be the same bin width for just keep things neat and tidy. And we count the number of points occurring in each bin. Well, that's how we generate a histogram. Now, some of you that have had courses in statistics may have come across a probability density function, which is a cousin to a histogram. We'll talk about those later on. Now, the histogram of the sine function, it has a nickname, and we're going to nickname it the bathtub curve. It's just a nickname. You'll see that in textbooks and literature. And what it shows is that the sine function prefers to dwell at its peak positive or its peak negative with a fairly rapid transition in between. When we get to fatigue analysis, these histograms will be very important. They're very important for random vibration. We're not doing random today, but we'll get to random vibration later. Okay, so earlier I talked to you about the Pogo and Michael Collins, and we did a Matlab script. Now it's time to actually dive in and find the underlying equations. Now, you may have been taking a calculus course many years ago, and one of the questions people ask, students ask, or their friends ask them is, hey, are you going to really use that calculus when you get to your profession? And you might ask yourself the same question as you're taking that course. Maybe you did. And the answer is, in shock and vibration, yes, we use calculus, we use differential equations, partial differential equations, Laplace transforms, Fourier transforms. We do all sorts of mathematics in shock and vibration, signal processing, and so on. So let's take a sine displacement function. X is a function of time. Now x is going to be the displacement amplitude, and we'll make it a 0 to peak. Then the sine function, the argument, omega is the angular frequency, radians per time. It's typically going to be radians per second in our world. And then we have t, the time variable there. So given this displacement, how do we calculate the velocity? Well, we take a derivative. So in your pre-calculus, you learned how to take derivatives. So x is going to go to v. V is going to be velocity. And this omega that's in the argument is going to come out and become a coefficient. And then this x, the 0 to peak displacement, comes straight down, and sine turns into cosine. Again, we just take the derivative of displacement to get velocity. It's pretty simple pre-calculus there. To get the acceleration, we do the same process again. So we've got the omega in the argument comes out once again and becomes omega squared. X comes down. Now cosine then turns into sine, and there's also a negative that comes out. So this is a matched set of consistent equations for displacement, velocity, and acceleration for the case of a simple pure sine function. And just to simplify, there's zero phase angle as well. Now, in the world of vibration, we're not so much concerned whether it's sine or cosine, and we're not so much concerned typically whether it's positive or negative. And I'm going to show you why here in the next couple of slides. So what we're concerned about is the peak values. Call them the magnitude if you like. So again, x will be 0 to peak. So what we just did in the previous slide, we can summarize in the top table there. There's displacement x, peak displacement, 0 to peak, and 0 to peak velocity is omega x, and 0 to peak acceleration is omega squared x. Now we can take this and turn it inside out, reverse it, whatever. What if we were starting off with a peak acceleration? That will be a, we'll call it a. Then the peak velocity, this is all 0 to peak still, the peak velocity is a divided by omega, and the displacement peak is a divided by omega squared. Now these set of relationships here in the two tables are very consequential for vibration analysis and testing. And I'm just going to show you an example here in the coming slide. So let's take a look off to the right, and let's say that we're going to do a vibration test on a shaker table, and it has to be a 10G test. It'll be sinusoidal 10G, 0 to peak 10G. Okay, that's all well and good. Let's start at the bottom row here so that we've got frequency in hertz and displacement inch, 0 to peak. So if we're going to test 10 Gs as a base input at 1,000 hertz, that displacement is a very low number. We might even say it's negligibly low. You'd have a hard time even seeing that with your eyes. You can fact check me on that by doing your own experiment. But what if we maintain 10 Gs, only now we're going to do a sine dwell at 100 hertz? So now we've got about, let's round that and say that's about 10,000ths of an inch displacement. Yeah, that's a little bit. You can probably see that with your eyes, but fairly minor displacement. We'll skip up a couple rows. What if we want to do at 10 hertz, maintaining at 10 Gs? Well, now the 0 to peak displacement is about 1 inch. Or 1 hertz 10 Gs, 97.8 inch. 0.1 hertz at 10 Gs, almost 10,000 inches there. Well, here's the situation. Our shaker tables, the typical ones we have in the lab, there's absolutely no way they can do 97.8 inches zero to peak displacement. That is just going to be impossible for any laboratory grade shaker. There are some university shakers that can do fairly large displacement for like scale models of buildings, but even those are going to be well shy of 97.8 inches zero to peak. So a typical shaker table might be, depending on the model, plus and minus 1 inch, maybe plus and minus 1.5 inches. Pay extra money, get the top of the line shaker, maybe plus and minus 2 inches. That's what our typical shakers can do. So in the world of vibration testing, we're not going to start at 1 hertz, not for an electromagnetic shaker. Typically, we're going to start at 10 hertz or 20 hertz for electrodynamic or electromagnetic shaker. And you'll see that in our PSD plots and our sine and sine sweep plots, because we want to limit the displacement because there's no displacement available down of that magnitude at those frequencies. Now, we're talking primarily about electromagnetic shakers. There are different types of pneumatic shakers and hydraulic actuator type shakers that can squeeze out a couple more inches of displacement. So if we do have a need to test down at 5 hertz or 1 hertz for, say, a transportation environment, we're most likely going to have to switch over to one of these pneumatic shakers. Maybe we'll talk more about them later on. This just shows a sample calculation, if you like your hand calculations. In this case, we've got a 2.5 G 25 hertz oscillation, sinusoidal, and we want to calculate the corresponding displacement. So this just goes through the mathematics. We've got omega then is going to be 2 pi times 25 hertz. We have to square that. We've got our 2.5 G. And this is just showing the 386 factor. So the English system is very awkward. And we're going to do a conversion factor, 386 inches per second squared per G, so that our final displacement is going to come out to be in inches and zero to peak. So 0.039 inches zero to peak. Some more statistics about sinusoidal oscillations. So the peak value is always square root of 2 times the RMS value. And the RMS value is always going to be 1 over square root of 2 times the peak value. These two equations work great for sine vibration, but they do not apply to random vibration. So when we get to random vibration, it's a matter of probability and statistics, and we're never exactly sure what the relationship between peak and RMS is going to be in random vibration, but there's some statistical things we can do to estimate what the peak value will be. More about that later on. So here is a spring mass system. And in the world of vibroacoustics, this is the most important model for component testing and analysis and design. So it's a single degree of freedom spring mass system. We will use this over and over and over again in this course series. That mass, m, you could call it inertia if you want, has an absolute acceleration, x double dot, and then the base has an absolute acceleration, y double dot. There's a spring stiffness k that comes from Hooke's law, and we've got a dash pod or damping element damper with a viscous damping coefficient of c. So this model is of vast importance, and we're going to be using this over and over again in our course series. So imagine a building subjected to an earthquake or an avionics component on a bulkhead or shelf or a panel where the panel is applying the base input to that avionics component. So we need to derive a governing equation of motion, and we're going to go back to Engineering 101 and use a free body diagram. Now there's a couple other ways, energy methods and so on, but let's just keep this very simple, and we're just going to use a free body diagram. So it's interesting, this mass, there is no direct force on the mass, but there are two indirect forces, or you can call them transmitted forces. So here we've got stiffness K, Y will be base displacement minus the absolute displacement of the mass, and that's in parentheses. And then similarly, we've got that viscous damping coefficient C, and then in parentheses, we've got the base velocity minus the absolute velocity of the mass. So now we're going to go to Newton's law, do a force balance, summation of the forces in the vertical direction, and we are going to come up with this equation of motion here. So there's the equation of motion. Now that equation of motion is interesting because it's not something that we can readily solve. Because very seldom are we going to know what y dot is, and very seldom are we going to know what y is. Let's go back to the previous slide. What we do know is y double dot. Well, that's the acceleration. That can come from, say, an accelerometer measurement. So it's fairly easy to measure or estimate what y double dot is going to be. But we don't know what y dot is or y is going to be. And you might think, well, that's no problem. We can just, we'll take that acceleration y double dot, we'll integrate it to y dot the velocity and integrate one more time to get the displacement y. Well, that's not going to work out so well because to really carry that out, we need to know what the y at 0 is and y dot at 0 is. So we don't know the initial conditions for y or y dot. So that makes this really tricky to solve for practical engineering purposes. Well, we've got a workaround. This workaround is very useful and efficient and effective. We're going to define a relative displacement z to be equal to the absolute displacement x minus the base displacement y. And we're going to go and do some substitutions and some algebraic manipulations here. And let's look at the second to last equation there. So that equation is, and we need to classify it in order to know how to solve it. That is going to be an ordinary differential equation, second order, linear, constant coefficients, and non-homogeneous. Well, the reason it's non-homogeneous is this minus m y double dot term there. Now you can call this an inertial force if you like, and then for convenience we divide through by mass, and then we get the equation at the bottom there. And we're going to do some further simplification on that equation. So we're going to take C over m, the viscous damping coefficient, divided by mass, and that's going to be equal to 2 times the viscous damping ratio times the angular natural frequency. Then K over m, stiffness over mass, is going to be the angular natural frequency squared. And we're going to do a substitution, and then we're going to come to our final equation there. You can see all the adjectives describing that equation at the bottom. And that's the equation that we're going to solve. Now, one thing that's really interesting about this equation is that once we know what the natural frequency is by test or analysis or estimation, and likewise we know what the viscous damping ratio is, well, there's no calculation method to predict damping. We have to either measure it or estimate it drawing upon databases. But once we know that angular natural frequency and the viscous damping ratio or have the estimates, we don't need to know what the mass is, and we don't need to know what the stiffness is. And that makes this a very versatile equation, very easy and practical to use. Well, next we're going to think about how do we solve that equation. So we've characterized all those adjectives there at the bottom, and those adjectives will lead us to a solution method. There's actually more than one solution method. If you go back to your differential equations class. So if y double dot is something well behaved like a pure sine or a half sine pulse or something that's fairly deterministic, or is deterministic in fact, we can use Laplace transforms, and that's how we're going to solve for z. So Laplace transform, it will be the preferred method of solving that class of differential equations in this course series, although there's another. The other method that I learned is we start with a homogeneous solution, and where homogeneous means set the term on the right equal to 0, and then we need to come up with a particular solution. So that method is also out there, but I favor the Laplace transforms. Now, once we know what z is, so we're going to solve for z, that's the relative displacement. Then we can take the derivative and get the relative velocity z dot, and take the derivative one more time, get z double dot, the relative acceleration. Now, relative acceleration by itself is not very useful, but when we add it to the base acceleration, then we get the absolute acceleration of that mass. So the two things we're looking for in terms of that spring mass response, what is the relative displacement? And you can think of that as being the spring displacement if you like. And what is the absolute acceleration of the mass? Those two output parameters are dependent variables. Now later on, we're going to be looking at another parameter called pseudo-velocity, but let's save that for later on. Well, what if y double dot varies arbitrarily with time? What if we bring in a random vibration signal or a pyrotechnic shock signal? Can we still use Laplace transforms? And unfortunately, no. But we do have a method. So if you're pulling out your differential equation textbook, this is what your textbook would say. So we're going to define something called a unit impulse response function, HT, for the homogeneous case. Now, I've got papers that go in all the detailed derivations. We're just doing a kind of an overview here. We come up with a unit impulse response function, and it's 1 over omega d. Well, omega d is equal to, it's called the damped angular natural frequency. It's equal to omega sub n, and then square root of 1 minus the viscous damping ratio squared. We've got an exponential decay term here, and we've got a sine term here. So what this really is, if we give like a velocity impulse to the system, what will its resulting displacement be? Well, in order to carry out the full solution to get the relative displacement, we have to use something called a convolution integral. You may have heard it referred to as a Duhamel's integral. And we're going to take this unit impulse response function, and we're going to embed it. Now, we're doing something kind of funny with the time because we've got this tau variable here, which is a pseudo time. So we're going to impose that kind of like a delay function there in for the time. So time changes to, in parentheses, time minus tau. You see that both for the exponential decay and the sine function. Now here we're going to put in our acceleration impulses, and we're going to integrate with respect to tau from 0 to the time of interest and divide by omega sub d, and that's the relative displacement. Now to carry out this calculation, for the case of digital data, we can come up with an equivalent digital form. Is very cumbersome because we have to, very labor intensive because we have to carry out that integration for each time of interest, t. So that is very cumbersome. You can write a Matlab script and do that calculation, but that's not what we're going to do for vibration analysis. So we have something that we're going to be using quite a bit during this course series, and it is called the Smallwood ramp invariant digital recursive filtering relationship. Now I've got links to papers I can share with you if you want to go and research that paper and read it yourself. This paper, the method, was intended for pyrotechnic shock. Well, guess what? It works for any oscillating signal whatsoever. So we can even use it for pure sine, although we don't need to. We are going to use this Smallwood ramp invariant digital recursive filtering relationship over and over and over again in this course series. This will be our go-to method for doing transient analysis. There are a few other methods out there, like the Newmark Beta method and the Runge-Kutta method, that we will talk about briefly. More so, we'll spend more time on Newmark Beta, and we'll only mention Runge-Kutta in passing. Runge-Kutta method does not work well for stiff systems. I know there's actually a family of Runge-Kutta methods. They don't work well for stiff systems, which we have in vibration analysis. So this is a numerical method. It's a very accurate one, by the way. And so we're effectively going to go this convolution integral, and we're going to represent it in a series format because we're going to have digital data, and then we're going to apply our Smallwood algorithm. So we're going to do a little exercise here, and it's partly to show you how a spring mass system will respond to a steady-state sine-based input in the time domain. And we'll solve for the exact solution using Laplace transform. And then just for fun, we're going to also solve for x double dot using our Smallwood algorithm. And we want to do this to develop confidence that our Smallwood algorithm can give us good results, because once we get to our random y double dot, a random acceleration base input, we're no longer going to be able to use Laplace transforms. Okay. Well, here is the famous Smallwood algorithm. And I'm not going to call out each of those terms one by one like a professor would at a university. But x double dot sub I is the absolute acceleration at time step I or time index I. So we're in the digital world now. And then we've got this coefficient here with all those terms times the acceleration x double dot I minus 1, which is the previous absolute acceleration response, minus this coefficient here times x double dot I minus 2, which is the absolute acceleration 2 time steps ago. Now delta t is the time step, and it's the inverse of the sample rate. And this method requires that delta t be a constant. So you can see delta t, time step, the angular natural frequency, viscous damping coefficient, and the damped angular natural frequency. And all of this kind of messy algebra here. Then we've got this term here times y double dot sub I, which is the absolute acceleration at the current time step, plus this coefficient here times the base input acceleration. The base input acceleration is always absolute at time step I minus 1, and this coefficient here times the base input acceleration y double dot at I minus 2. So 5 terms on the right-hand side. So the reason we say this is recursive is these first 2 terms, because the response, the absolute acceleration response at any time step, depends in part on its response at the previous 2 time steps. Now, in the world of control systems, this would be called a feedback loop. And feedback loop helps the control system to be stable. Feedback does not guarantee stability, but it greatly enhances the probability that the control algorithm will be stable. Feedback loops also occur in the context of electrical filtering, like when we get to our Butterworth filter later on, we'll talk about the feedback loops for Butterworth filter. So this is obviously digital data, it's recursive, it's filtering because the spring mass system itself acts like a filter. We'll be talking more about the mechanical filtering aspects of the spring mass system as we go along. But basically, it's some base input frequencies. There's our system again. At some base input frequencies, y double dot, let's say y double dot is equal to 1. X double dot might also be 1 at certain frequencies, and that's called a unity gain. At other frequencies, x double dot will be much greater than y double dot, such as the case of resonant excitation, particularly that case. And for other frequency cases, x double dot may be less than y double dot. And these are all in reference to peak magnitudes, by the way. So this spring mass system is a mechanical analogy of an electrical filter that could be made up using resistors, capacitors, and inductors. We won't do that, we won't go that far today, but that's something you could look into for homework. So we are going to apply a y double dot steady state sine. It'll be 1g, 10 hertz, and the natural frequency of the system will be 10 hertz, q is equal to 10. So we are purposely going to drive this into resonance. We're going to use both the Laplace, which is the exact, and the Smallwood, which is the approximate solution methods. And we're comparing the results of Laplace and Smallwood in the next couple slides to gain confidence in Smallwood. So a special case of resonant excitation of the spring mass system, which, by the way, in aerospace we want to avoid because we get those high x double dot acceleration responses that could potentially lead to a fatigue failure or something like that. Okay, so we're going to go back to our Matlab GUI, to structural dynamics, to spring mass systems, single degree of freedom, and we're going to do a classic shock-based input. Now, we're not actually going to do shock, but the function that we want to go to is under the classical shock-based input. You'll see what I mean in a minute. So we go to this classic shock-based input, and there's our spring mass system. This is set up, let's do a half sine pulse or terminal sawtooth pulse or whatever. Well, for convenience, I also put in a steady state sine. So let's see, we've got English units, and acceleration for y double dot is 1g, 10 hertz. Duration will be 4 seconds. Q value is equal to 10. And Q value equal to 10, that's called the amplification or quality factor, and that's equivalent to 5% damping. So if we want to calculate the equivalent damping, we would say, okay, let's take 1 over, and then in parentheses, 2 times Q, and that works out to be 5%. Or we could say that the Q value is equal to 1, and then in the denominator, 2 times 0.05. Okay, relative velocities and relative displacements. Now we don't know the base input's initial displacement. We don't know its initial velocity for base input, but we can say that the relative velocities are both equal to 0. We'll do a time history response. We'll do a 10 hertz. We're going to calculate, and then after you do the calculation, you'll see the plot, and go back and let's save the base acceleration as base, because we're going to need it for the part 2 of this exercise. Now, what I also want you to do after you get done saving base acceleration as base, I want you to take response acceleration, and I want you to save that as Laplace response. So there's 2 things you need to save. I'm only showing one screenshot there, but that should be pretty straightforward. So let's go ahead and do that calculation, and you'll see several plots pop up. Here's the one we're going to focus on. Got acceleration g versus time in seconds. And at the top, I'm duly noting that the natural frequency is 10 hertz, Q is equal to 10. And then the peak response. So the red curve will be our base input, the steady state sine base input, 1g, 10 hertz. And then the blue is the absolute acceleration of the response. So there's a little transient segment here while the cycles build up to steady state. And then at steady state, the peaks are plus and minus 10 Gs. A couple interesting things you can see when steady state is reached, that the response is lagging the input by 90 degrees. Now, another thing we see is that the peak response is 10 Gs, and the base input's 1 G. If you take that ratio, that's the same as the Q value. But I want you to be very careful about getting comfortable with that rule. This is a very special case of a spring mass system driven into resonance. It's a single degree of freedom system. So this is not a good way for experimentally extracting Q. So let's say that this is all measured accelerometer data, which it's not. It's just in chemistry, what we just did would be called a dry lab. We just did a dry lab experiment. But let's say that we measured the blue curve and the red curve. This was for a shaker table test for a single degree of freedom system with natural frequency 10 hertz, Q is equal to 10. And you wanted to say, oh, let's go back and estimate what the Q is by taking the peak of the response and dividing by the peak input of the red. Well, don't become too comfortable with that, because once we get to multi-degree of freedom systems, we're not going to be able to do that, or continuous systems, we're not going to be able to do that. So we've got more robust methods for extracting Q from measured data that I want you to use, like the half-power bandwidth method and a couple other methods we'll talk about later on. Well, this is all the Laplace, and that blue curve, I'm saying the blue curve is exact. Well, it's only exact to the extent that our model is exact, but per our idealized model, the blue curve is exact. Of course, both the blue and red curves are really a series of dots with straight line segments from one dot to the next for the respective curve. Well, let's go ahead and do our Smallwood. Let's set up for Smallwood. So we're going to go back to the main GUI, structural dynamics, spring mass, system, single degree of freedom. So previously we're at classical shock base input. Now we're going to go down one to base input in the time domain. Click Analyze. Okay, so this script calculates the response of a single degree of freedom system to an applied force or base excitation frequency. And this is going to be, you can see small, we'll get to that in a minute. So we're going to go and take a look, and we've got a couple, in our workspace, we've got a couple arrays. We want base. Now, if you don't see base there, either you didn't save it, or maybe you need to click on Update List. 10 hertz natural frequency, Q is equal to 10. Stay with English units. Now we've got our choices: base acceleration or applied force. We'll do applied force later on. Today we're doing base acceleration. So there is our spring mass system, and you can see that our numerical engine is the Smallwood ramp invariant digital recursive filtering relationship. It's approximate, but very nearly exact. So hit our calculate there. A whole bunch of statistics coming up. We'll pay more attention to those later on. And here is the Smallwood results here. Acceleration g, time in seconds, and it looks pretty similar to what we saw before for the case of the Laplace transform. So you can see once we reach the steady state, the response is lagging the input by 90 degrees. And the response is very, very nearly getting up to plus and minus 10G peak. It's actually 0.3% shy. We'll talk about that in a minute. Because this is an approximation method. It's a nearly exact approximation method. It's a numerical technique. So we're going to save, we're going to do some saving here. We're going to save the response, the absolute acceleration response. So before we were at the Calculate tab, now we have to go over to the Export and Post-Process tab there. And we're going to export this as absolute acceleration. It'll be the Smallwood underscore response, and we'll save that. So again, Export and Post-Process, Export absolute acceleration, Smallwood underscore response, click on Save. Okay, big moment of truth coming up. We'll go back to the main GUI. We're going to go to Plot. We'll do Multiple Curves Alt. Plot 1 there. And we are going to plot two curves, and the top will be Laplace underscore response. Legend Laplace, click on the plot. Followed by Smallwood underscore response, Legend Smallwood. Click that checkbox. Title, I'm going to call this SDRF response, natural frequency 10 Hz, Q is equal to 10. Time in seconds, acceleration g for the two labels. All these we're going to do as defaults for right now. Later on when we do this, we'll be doing like log plots, and we'll do manual limits for x and y axes, but just take all the default parameters for now and click on Plot Curves. Now this is the moment of truth, because we have acceleration g versus time in seconds. We've got the red curve is the Smallwood and the blue curve is Laplace. And you say, hey, wait a minute, I only see a red curve there. Where's Laplace? It doesn't seem to really be there, right? That's actually a good problem, because those curves are so nearly identical that at this scale, it appears just to be all the same thing. Well, if we go in and zoom in a whole bunch of times there, so that's what I've done. You can see two of the positive peaks there. And the data is digitized at a certain sample rate, so you can see the effects of the digitization. And there's 2 points there for that peak there. Well, maybe we should have doubled the sample rate, and we could have come up with a midpoint there. It would have been more, just a little bit more like a rounded off sign. That's kind of a fine point for what we're doing here. So the Laplace did reach plus and minus 10 with the sample rate shown, and Smallwood is 0.3% lower. Well, that's because Smallwood is a numerical approximation. I'm actually very happy. If I can use a numerical technique and come up with within, say, 0.3% difference, that is a good day. So we are going to use, we'll only use Laplace transform for special cases like sine and half sine, but Smallwood we're going to use extensively for whatever we can throw at the base input: random, sine sweep, pyrotechnic shock, stationary, non-stationary, random, hybrid environments, sine on random, sine sweep on random. Smallwood is going to be, again, our go-to method, and we've developed confidence in it through this exercise here. Okay, we've got one final exercise to finish up today. We're going to go to import data, acceleration time history. This is a library function. We'll go to channel beam. So this is going to be a cantilever channel beam, and an impulse was applied to the free end, and it was allowed to undergo free vibration. And we're going to take a look at its free vibration response. Now, a channel it refers to the cross section. And so imagine you've got a C-shaped cross section, only instead of a smooth rounded, you're going to square off the two corners. You can think of it that way. So we're going to go next to signal analysis, and we're going to go to time history and acceleration, sine and damp sine curve fit. So we were at this function previously when we were doing the Pegasus drop transient in a previous unit. We go to this curve fit here and we find our channel array. So this is going to go out to the workspace and find out, okay, what are the available time histories? So you should see channel there. Again, sometimes you have to click update list. So we'll call it a plot title channel beam, y-axis acceleration. Actually, that should be acceleration G. I'll have to go back and fix that. And we're going to plot the time history, and we're going to do this time history actually is going to be from 9.4 to 9.6. And then the maximum frequency is going to be 4,032 hertz, and we're just going to keep that as is. We're going to go to the damp sine. So by now, if you clicked on plot time history, you should have already seen the time history. And it's primarily composed of two damp sines. And zero delay option means that the delay time for each will be 0. So each of the two damp sines is going to begin at 9.4 seconds. And let's just hit the calculate button. And we get acceleration. It's supposed to be in G's, time in seconds. And you see the red curve there and the blue curve there. And the two curves are matching up very well. If you really squint your eyes and turn your head a little bit, you can kind of see a little bit of difference between the blue and red curves. But those are matching up so well, so that gives us confidence that we have a good curve fit. So as we go to the results, so the results, you have to go to this tab over here, view results. So I did that and took a screenshot. We're not interested in phase angle today. We could be interested in the relative amplitudes, but let's focus on the frequencies. So this is actually a beat frequency effect. We've got two closely spaced frequencies, 582.7 and 690.8 hertz there. Now their damping ratios are extremely low damping. Those are well below 1% damping. In fact, they're both below a tenth of a percent damping. Very, very low damping there on this aluminum channel beam mounted in a cantilever configuration. Now let's take a look at those two frequencies. We can take the difference in those two frequencies, and that's going to be called the amplitude modulation frequency. So if you were to just imagine drawing an envelope, kind of a sinusoidal envelope to cover the peaks, the positive peaks there. So you'd find if you do that signal, that envelope signal, and you went from like one peak set to the next and to the next and to the next, and come up with an equivalent frequency, that would be 108 hertz. The two frequencies in the results box are natural frequencies of that cantilever beam. Now let's consider a hypothetical RF coupler, which is a small electronic component, and it is to be mounted at the free end of the beam. So we've got those two frequencies, 582.7, 690.8. There's actually a third frequency at the bottom. It's 108 hertz. Now that's the difference between the two frequencies in the results box. So that is the frequency of the amplitude modulation. Now let's go back to this hypothetical RF component mounted at the free end of the beam where this accelerometer was mounted, by the way. What do we design, analyze, and test for in terms of base input and the frequencies thereof? 582.7 hertz, 690.8 hertz, or 108 hertz. So those are three choices, and we could also have some combination thereof. So what do you think the answer is in terms of what frequencies do we need to account for? And the answer is a combination thereof, and it's the two frequencies in the result box. So we do not need to design, analyze, and test our RF component to 108 hertz. Now the human ear, if you were listening to this free vibration, these two natural frequencies, your human ear would pick up 108 hertz. And that's just due to our sensory system and the way our brain processes those signals. So you definitely hear that, but it does not really exist. It's just a psychological effect. And that concludes the sine vibration unit. And the next topic we'll be considering next time will be sine sweep. So please come back for more fun. Thank you, and goodbye for now.